So what we will need to do is that we will, at every time instant, and instead of just estimating all the time at once like that, no, I will be looking at every time instant and estimating all the frequencies such that I get how the vectors look like at every time point, and then I will draw these actual vectors, like the real vectors, and I will add them together. So the idea in linear algebra, if you add two vectors like that, it will be like if you took this vector and you just stick them together like so. So the idea is this: if these are our vectors and they are looking like that, the summation of this will be going like this. I'm just taking this vector and this vector and this vector. Okay, when you add them. So if this is your origin 0 0, if you are adding them, you are sticking them together like that, and you see the position of this end point, this tip of this arrow, and you just, or end effector if you are really into robotics, and you would say that, okay, this point corresponds to something on the x-axis, something on the y-axis, a real value and imaginary value basically, and that's how you will estimate your signal, because we know that to estimate the first point, what we did was just rotating these vectors and add them together. So if we visually add them together, this end point is the summation of the vectors at a very specific time point, right? So the end effector will be the amplitude of the signal. So we can basically sum them, visualize them, and we know that the ending part of the summation of these vectors will be drawing our signal. And that's exactly what I am trying to achieve in this part here. So in this one, we would see that I'm getting my coefficients as we did here. Right now I'm looping over time, so I'm looking at every instant of time and estimating all the frequencies such that I know the position of the vectors at an instant of time. Okay, so after doing so, we can look at what is happening and see how it looks like. So we would look at this and this part. Okay, if you would like to see what I did with this one, it's completely up to you, but the main idea here was that we don't have imaginary part, so I had to have some kind of trick to visualize these vectors. So what I did here was that, and instead of visualizing the real and imaginary part, we don't have imaginary part, we only have real, so it will be not leaving the x-axis and we wouldn't see anything. So what I tried to do instead, I tried to take the value on the real axis. So okay, so let's look at this in a different way. So what I try to do with this, and instead of having the real and imaginary axis, I try to visualize this in a different way. So because we're not leaving this axis, we wouldn't see anything. Our vectors are always rotating on the real axis. Okay, so what I tried to do, we know that the end effector, the ending value of the summation, will be representing the amplitude of the signal. So what I did, instead of representing the end effector or representing the values combined together on the x-axis, I actually represented it on the y-axis. Okay, and I am plotting the signal in the same time on the y-axis. So right now the y-axis will have the amplitude of the signal, okay, and this will be time, the x-axis will be time. Okay, and what I did, I took the real value, okay, of our vectors and put it here. So you would basically see that our vectors will be rotating on the y-axis and they are added together on the y-axis, but we are still facing the same problem, that we don't navigate or explore the x-axis, we're not leaving the y-axis. So what I did next, I extended the representation of these vectors into number of points that equal the length of the signal. What I mean by that, I took these vectors, rotating vectors on the y-axis, and I extended them into 100 points. So you would see vectors added together like that, and they are going to the end effector position, and this end effector position is actually drawing the amplitude of the signal because they are added together to the amplitude of the signal, right? They are added together at an instant of time to give the amplitude of our signal. And then I proceed with that. So I shift them, and I keep showing them such that we would, the next instant of time, would see that they are here and drawing this point. The third instant here and drawing this point, and so on. So right now you will be able to see the actual vectors that are drawing our signal. Okay, so I think that's nice to see, and please feel free to trace this code. I will just give one little tip, that maybe the challenging part was to draw these vectors, because if you draw this first vector, you will have, let's say, origin at here, but if you are drawing the second vector, the origin will be the tip of the previous vector, and you will have to do a cumulative summation, and that's what I'm doing here, a cumulative summation of this, because right now the coordinates of this will depend on the previous tip, such that it's always updating like that. So we would need a cumulative summation of the vectors. If you have any questions, please go ahead and write me an email or a comment below, and I will be happily replying to this. So here I'm just changing the limits, like the x limit and y limits, and visualizing our data. So let me run this in a second time. Okay, so right now I'm just visualizing this. As you can see, these are the vectors that we are talking about, and these are the points of our signal. Okay, so these are signal. Let's run it a second time. Okay, and see, these are the vectors, and they are going to the position of the end effector, and they are rotating to draw this signal at each time point. It's just very nice to see the vectors in action at every time point and how they are estimating our signal. Okay, so I really wanted to take this a step further, and I really think this will be a nice way to visualize our data and look at the complex waves as well. So right now let's consider a complex signal, and I promise actually thinking about this complex signal will be much easier than plotting the real signal and doing this kind of trick, because with the complex signal you have a real part and the imaginary part. So the thing is, you already have what you are looking for. So here I'm just constructing a signal, so it will have this form, cosine plus I sine. And this signal is now 3D. What I mean by that, you have a real part, imaginary part, and you are progressing in time. So we can almost think of this as having the real, the x-axis, and the imaginary or the y-axis, and you have then progression in time in z dimension. Okay. So again, we have our sampling rate 100, changing the time, and we have frequency, and then we have the amplitude of our signal, and in here I'm just creating the signal a cosine 2 pi ft plus I sine, and using this we will be able to see real part of the signal and the imaginary part of the signal if we would like, and I will try to do this right now. And we are still estimating Nyquist, and then changing our units in hertz, and then I'm here plotting the time with the real part of the signal, so this will be in blue, and the second part, the imaginary part, will be in red, and we can look at this and see that this is true. We have amplitude of 3, so that's why this is touching 3, and we have a cosine wave to be real, so that's a cosine wave. Okay, and we have a sine wave that is imaginary, and that's the sine wave. Okay, right now we have our complex signal, cosine plus I sine. We have real part and imaginary part, and we need to see the Fourier transform of this, and recover our signal, and it will be very, very nice to see our vectors and how they are added together. But with this one, we will do something nicer. We will see the rotating vectors in 3D space and how they are drawing our signals. Okay, so let's continue with this. Here I'm just plotting the frequency spectrum of this, and then here we are doing the inverse Fourier transform and then getting our signal back. Okay, what happens here is similar to what happened before. We are getting the coefficients, okay, and then we are rotating them. So right now we know that this is our uh, initial configuration of the vectors, and all that we need to do is to rotate these vectors. So right now I'm taking a specific time point, estimating all frequencies, and this will have all the frequencies that we want. And then here I'm not doing any tricks. I'm visualizing the real and imaginary part of our vectors, because we are having 3D space. I'm creating an origin of 0, 0, 0, and then plotting this using this plot3 function, and you are plotting, of course, the origin and then the real part, and then imagine the real part, imaginary part, and progression in time, which is an index using this nice iterator J, which is looping on the time. So we can see what happens is that here I am plotting each individual vector. So basically when we end this loop, I'm here plotting all of our vectors together. So this will go around 100. You see, this is this is the second vector added to the first vector, and so on. You see, we are adding the vectors together. So the first one was here, and the second here, and the third is here. It's so on. You see, all of these vectors are being drawn and added together to go in a specific position. And let's just finish all of this, okay? All of these vectors are added together to go and draw our end effector point, okay? So right now, let's extend this and see the very nice visualization of this amazing Fourier transformation. Right now we will have real and imaginary and time progression. So I will leave this animation to play. You would see that this is the real part, imaginary part, real time progression, and these are the vectors. Each time we are plotting more than 100 vectors added together to go to the position of the end effector and plot our data point. I really like this. I really like this Fourier transformation. It has limitless applications and it's very handy in different fields. It's a very important concept to understand. Okay, and because we are drawing cosine plus I sine, then we know something. We know something. We know that the relationship between the real, which is cosine, and the imaginary, which is sine, if we don't look at the time progression, it will be like a vector rotating, and that's what we discussed in the previous video. If we have a unit circle rotating and we have x-axis cosine and sine axis and the sine on the y-axis, then we would have a rotating vector inside a unit circle. And if we look at this from above, that's exactly a circle. And this circle is not going to 1, it's going to 3, because remember our amplitude of the signal is 3. Okay, so it always goes to the maximum amplitude. So from -3 to 3, from -3 to 3. Okay, and in the time progression, you can see how this is really going on in time. And we could see in the beginning the vectors that were drawing this, and feel free to, of course, replay this many times and try to think about it. Okay, and the nice thing is we know that the real axis is plotting a cosine, and if you look at the beginning point, this is going from 3 and then going to -3. So this is cosine, because cosine is going at time 0 at the beginning, is going from the maximum amplitude. Okay, so we can almost get rid of this imaginary axis. So let's make this axis actually like that, like going inside the screen, so we don't look at the imaginary axis. Let's look at this cosine alone. Cosine is real, and cosine is actually going from the, in the beginning, going from the maximum amplitude and then going like so, and that's a cosine. That's a perfect cosine wave progressing in time like so. Okay, so let's not consider the real part, let's consider the imaginary part and see the progression in time. It should be a sine wave, right? So instead of beginning from the maximum amplitude, it should be beginning from zero, because there is a pi over 2 phase shift between the two, so it should be beginning from zero. Okay, so let's see how the imaginary part look when we bring it like so in the time progression. And we can see that yes, it's really starting from here, from zero. It's going to the maximum and then going down and so on, and that's a sine wave. So it's a very nice way to see how this is progressing and how these vectors are rotating to draw our signals. I think that now we can appreciate the importance of the Fourier transform and cosine and sine waves, because not only cosine and sines are good for estimating the relationship between lengths and angles, but also they can create waves. They are essential for creating waves, and the applications of the Fourier transform are absolutely amazing. Like even the video that you are watching right now is going through some transformation such that it's getting compressed and getting stored in the frequency domain, and then on your end it's being transformed using the inverse Fourier transform to be displayed again, and we can go to the frequency domain and do some cleaning or getting rid of some frequencies, such that we are compressing our signals and just storing the frequency domain information, and then we can easily apply the inverse Fourier transform and go back to time. So the applications of the Fourier transform are limitless. It has a lot of applications in different fields, and all of that is coming from our lively rotating vectors. Thank you so much for listening and watching this video, and I hope to see you in the next one.